And now we embark on the journey, which is 2.5. So 2.5, we're going to be, if you're coming to classes, it's going to be taught over 2 days. And it's going to be a series of 6 videos, so we can do little bits at a time. So what we're going to build up to is being able to do 4, kind of 5 transformations. We're going to do A, B, C, D. Now, if you are working with the textbook, if you like to do things in the order that the textbook does, I'm different. I like to teach you left to right, because when we put them all together, that's the order that we're going to do the transformations in. So I'm going to start with A, move on to B, kind of do A and B together, and then I'm going to go on to C, I'm going to do D, and then I'm going to do C and D together, and then we're going to do A, B, C, D all together. Okay, so the first thing we're going to talk about is the A. The A value is a transformation on Y, and this is super important, okay, because there's going to be certain ones that are transformations on Y and certain ones that are transformations on X. So A, this value out front of the f of x, is going to be a transformation on Y. Let's see what it does to a graph. And I'm going to do that by pulling up Desmos. I love Desmos. I love seeing graphs in action. So let's start with a graph simply like y equals, let's go x squared. Okay, let's start with something we've already been comfortable with. Putting in an A transformation is putting a value in front of the entire equation. So something like y equals 2x squared. And what do you notice that this did to this graph? Now, if you took Math 50, we've already talked about this. You should notice that normally in an x squared graph, we go over 1 and up 1, right? So we have this point here, 1, 1. This value of A stretched my y value by 2. So instead of going over 1 and up 1, I go over 1 and up 2. Normally I go over 2 and up 4, and instead, so over 2 and up 4, I'm going to go over 2 and up 8. So it's taking all my y values and stretching them. And so we call this a vertical stretch. When we were talking in Math 50, we said that it made my graph narrower. We're going to move to more Math 60 terms. We're going to say that my graph has been vertically stretched. So when I have an A value that's greater than 1, it stretches the graph. So even if I do something more complex, let's do y equals the square root, sorry, my keyboard sometimes gets a delay, square root of x. Okay, so if I was again going to do this A transformation, it would be y equals, let's put 5 times the square root of x. And you'll notice that again, it stretched it vertically. Normally in a graph like this, we'd go over 1 and up 1, and instead we go over 1 and up 5. So it stretched it vertically. Okay, so this A value, that's its job. Well, what if we change the A value from being a value greater than 1 to a value between 0 and 1? So what if we do something like a half? Instead of stretching my graph vertically, this textbook likes to call it a vertical shrink. I like a compression. I'm like, you stretch it, you compress it. This textbook says you vertically stretch it versus you vertically shrink it. So we've taken it, instead of going over 1 and up 1, it's only going over 1 and up half of that. Normally we'd go over 4 and up 2, instead of we go over 4 and up half of that. It's taking all of these y values and timesing them by a half. Okay, so let's go back to the note. So in our note, I've shown you 2 examples of this. So the first example is a graph of y equals x cubed minus x, which we'll call y equals f of x. The transformation, doing a value of A, again would put a 2 out front of everything. Okay, so 2 times x cubed minus x, and you would end up with this graph that got vertically stretched. Okay, all the y values, the only y values that stay the same are when y is 0. So all your x-intercepts remain the same, and then everything else gets stretched. So y equals 2 f of x is this green graph. Versus when we do an A value between 0 and 1, my graph gets shrunk vertically, so along the y-axis. So you'll notice here again, the x-intercepts stay constant, but the graph got shrunk. It got closer to the x-axis. Okay. So an A value, when the A value is greater than 1, the graph is vertically stretched. When the value of A is between 0 and 1, the graph is vertically shrunk or compressed. Okay, so if you want to obtain a point on your graph y equals a of f of x, you multiply the y coordinate of the original graph by a. So for example, with this one, actually, no, we'll just do it down here. So for example, with this guy, so if I have a point 2.8 on my original function, 2.8 on my original function, on my base graph, and I want to find the corresponding graph on my transform function, g of x, what would it look like? Well, g of x is equal to 2 times f of x. This is going to multiply my y value by 2. So I'm going to take my y value, I'm going to multiply by 2, and my new point would be simply 216. I'm vertically stretching it. How can I describe this transformation? I would say it is a vertical. I'm going to stop writing the whole word vertically and just put v dot. It's vertically stretched by 2. All right, what about this one? So if my original point is 2.8, and I know that the a value multiplies my y values, it means I'm multiplying my y values by 1/4, or I'm dividing my y value by 4, right? Same thing. So my new point would be 2, 2. We would call this vertically shrunk by 2. Oh, sorry, not 2, 4. Okay. What about this last one? So again, sometimes they talk in terms of a function like f of x, and sometimes they talk in terms of a base graph, and we'll talk about the base graphs in a second. Actually, no, let's talk about it now. So you are expected to be comfortable with these 7 base graphs. There's y equals x, which your textbook calls an identity function, and I've always called a linear function. There's y equals x squared, which your textbook calls a squaring function, which I've always called a quadratic function. There's the square root function. There's the cubing function, cubed root function, reciprocal function, and absolute value function. This one might be new to you. We didn't really graph it in my Math 50, so let's talk. And I purposely didn't ask a lot of questions about it, specifically graphing, because I don't really expect you to know that one. But what I want to do is talk about some features of these. So you're expected to be able to reproduce these. These are going to be what we call base graphs that you are going to transform. So a y equals x graph, if we look at a couple points, you'd have a point 0, 0. You'd have a point 1, 1. Ooh, that looked horrible. You'd have a point 2, 2. Right? You'd have a point -1, -1. And you can get these points using a table of values. -1, -1. You can get these points using a table of values as well, but I just want to kind of show you a few key points. For your quadratic function, it starts at 0, 0. It goes over 1, up 1. It goes over 2, up 1, 2, 3, 4. So those are some key points. And then it's got symmetry over the y-axis. So you'd have a point -2, 4, -1, 1. This guy, a couple key points are 0, 0. This point here of 1, 1, and then I would jump to 1, 2, 3, 4, and 2. So again, if these are not comfortable with you, you might have to do a table of values to start, but if you at least just take these points that I've written down on here, that would be a good place to go to. Y equals x cubed goes 0, 0, over 1, up 1. If you put in 2, you go over 2 and up 8. So there'd be a point 2.8 over here. And this one has origin symmetry. So you'd have a point -1, -1, and you'd have a point -2, -8 as well. All right, your cubed root function, same idea. You'd have 0, 0. You'd have 1, 1. And then you'd all go all the way over here to 8, 2. And then it's an odd function. Well, no, I'm not going to say that. It's not an odd function, but it does have origin symmetry. So we're going to have a point -1, -1, and we're going to have a point -8, -2. All right, reciprocal. All I'm going to say to you is that there is a point 1, 1 here, and there is a point -1, -1 here. Then from here, what you're going to do is pretend there's like dots on your axes and just make your graph approach it. So that's your basic sketch. Just go whoop, 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 whoop. We'll talk way more about that later. Absolute value function. If you put in x value as 1, you get a y value of 1. If you put in an x value of, what am I at? 1, 2, 3, 4. Let's say 5, you get a y value of 5. And then there's y-axis symmetry. So -1, 1, -5, 5, and everything in between. Okay. Moral of the story is these 7 base graphs, be comfortable with them. Okay, you should be able to sketch them and then transform them. So here, you should recognize that the base graph is y equals x cubed. So then how's it changed? Well, we put a 3 in front. Okay, so this is meaning my y values are going to get times by 3. If I had a point 2.8 on this graph, my original graph, I would times the y value by 3, and I would now have a point 224. It is a vertical stretch by 3. All right, so I'm going to do 2 with you, and then you are going to go and practice these on your own, like just this little skill, and honestly get good at each one. So practice these vertical stretches and shrinks, and then move on to the next one. And I've created a worksheet. I find the textbook delves pretty deep pretty quick, so I've created a worksheet that'll be in your course package, so that you have the graph to do it on, and maybe you'll be more motivated to do it. And I would really like you to do those worksheet questions first, and then you can jump into the textbook questions. I've tried really hard to pick specific questions that only do a vertical stretch or shrink. If I've messed that up, please just let me know. Okay, so let's do these ones together. So what we're doing when we're doing these vertical stretches on a base graph, so this is an f of x graph. I don't know the equation of it. I can't use a table of values. Like this one, really, I could just plug in values of x and solve for y. This one I can't. So you have to be able to transform points. So what I like to do is pull out those key points. So there's a key point here at at negative 5, 0. The next key point, so this kind of has the same shape. It's increasing function until you get to negative 1, 4. That would be the next key point I would look at. Then I have another key point here at 1, 4. So I'm going to write it up there. Keep it clean, keep it clean. And then we'd have another key point here at 4, 1. So when you're transforming graphs, you want to look at just transforming a few points that will give you the overall shape of the new graph. And then you do the transformation. This tells me to take my y values and times them by 2. So I'm going to take my y value, I'm going to multiply by 2. 0 times 2 is still 0, so that point doesn't change. Then I'm going to take this one, I'm going to multiply the y value by 2. This point would now become negative 1, 8, so it's going to go up to here. Then I've got this one, I'm going to multiply the y value by 2. It's going to be a 0.18. So it's going to be up here. And then I've got this point, I'm going to multiply the y value by 2. X value stays the same. And you get 4, 2. 4, 2. And then you just connect the dots. And so you go up to here with a ruler, of course. Then you go across to here. And then you go down to here. So I didn't have to transform every single thing. Like I didn't take this guy and multiply it by 2. And I would have done a way better job of graphing it if I'd used a ruler. But the key thing is you can see that this graph has been vertically stretched along that y-axis. Okay, so now I've done this one for you where I've drawn the base graph, but you're expected to know y equals the absolute value of x. So that's what you would graph first. This is y equals the absolute value of x. Then you have to know that this transformation is that I'm going to take all the y values and times them by a half. So this point here, 0, 0, is going to stay the same. So 0, 0, if I multiply the y value by a half, it stays 0, 0. But then we pick another point. I'm going to pick this point here at 2, 2. And I only need a few points to give me a good representation. Times the y value by a half or divide by 2 and I get a new point, 2, 1. So it's going to go half as high. Maybe I pick this point here at 4, 4. I times the y value by a half and I get 4, 2. So this point here would go 4, 2. And that should be enough, especially if I'm using a ruler. I don't have a ruler on here, so I'm going to go 4, 3. Or sorry, 6, 3, and I'm going to go 8, 4, just to give me some more points. And then I'm going to connect those. Actually, I'm going to try. I found this new function. So if I go here, sometimes it doesn't work. I want this line. I want it to go from here. Yeah, no, never mind. I'm just going to try my best. So I'm going to go through these points. And then I know that this graph has y-axis symmetry, so I'm just going to mirror these points on the other side. So I'm going to go over 2 and up 1. I'm going to go over 4 and up 2. I'm going to go over 6 and up 3. And I'm going to go over 8 and up 4. And this is my new transformed y equals 1/2 absolute value of x graph. All right, go and practice this transformation, and then we'll move on to the next video.